1.6 The Raisin Cookie Model of the Atom. I wonder if this is plum pudding model. Okay. The Raisin Cookie Model of the Atom with 4 units of charge, which we now know to be beryllium. Based on his experiments, Thomson proposed a picture of the atom which became known as the Raisin Cookie Model. In the neutral atom, shown in the figure, there are 4 electrons with a total of -4e, sitting in a sphere, the cookie, with a charge of +4e spread throughout it. It was known that chemical reactions could not change one element into another, so in Thomson's scenario, each element's cookie sphere had a permanently fixed radius, mass, and positive charge, different from those of other elements. The electrons, however, were not a permanent feature of the atom, and could be tracked on or pulled out to make charged atoms. Ions. Josh. Although we now know, for instance, that a neutral atom with 4 elements is the element beryllium, scientists at the time did not know how many electrons the various neutral atoms possessed. This model is clearly different from the one you've learned in grade school, or through popular culture, where the positive charge is concentrated in a tiny nucleus at the atom center. An equally important change in ideas about the atom has been the realization that atoms and their constituent subatomic particles behave entirely differently from the objects on the human scale. For instance, we'll see later that an electron can be in more than one place at a time. The Raisin Cookie Model was a part of a long tradition of attempts to make mechanical models of phenomena, and Thomson and his contemporaries never questioned the appropriateness of building a mental model of an atom as a machine with little parts inside. Today, mechanical models of atoms are still used. For instance, the Tinker Toy-style molecular modeling kits like the ones used by Watson and Crick to figure out the double helix structure of DNA. But scientists realize that the physical objects are only aids to help our brains, symbolic and visual processes, think about atoms. Although there was no clear-cut experimental evidence for many of the details of the Raisin Cookie Model, physicists went ahead and started working out its implications. For instance, suppose you had 4 electron atoms. All 4 electrons would be repelling each other, but they would also be attracting toward the center of the cookie sphere. The result should be some kind of stable, symmetric arrangement in which all the forces cancelled out. People sufficiently clever with math soon showed that the electrons in a 4-electron atom should settle down at the vertices of the pyramid, with one less side than the Egyptian kind, i.e. regular tetrahedron. This deduction turns out to be wrong because it was based on incorrect features of the model, but the model also had many successes, a few of which we will now discuss. Example: flow of electrical charge in wires. One of my former students was the son of an electrician and had become an electrician himself. He related to me how his father had refused to believe all his life that electrons really flowed through wires. If they had, he reasoned, the metal would have gradually become more and more damaged, eventually crumbling to dust. His opinion is not at all unreasonable based on the fact that electrons are material particles, and that matter cannot normally pass through matter without making a hole through it. 19th century physicists would have shared his objection to a charged particle model of the flow of electrical charge. In the Raisin Cookie Model, however, the electrons are very low in mass, and therefore presumably very small in size as well. It is not surprising that they can slip between the atoms without damaging them. Example: flow of electrical charge across cell membranes. Your nervous system is based on signals carried by charge moving from nerve cell to nerve cell. Your body is essentially all liquid, and atoms in a liquid are mobile. This means that unlike the case of charge flowing in a solid wire, entire charged atoms can flow in your nervous system. Example: emission of electrons in a cathode ray tube. Why do electrons detach themselves from the cathode of a vacuum tube? Certainly they are encouraged to do so by the repulsion of the negative charge placed on the cathode and the attraction from the net positive charge of the anode. But these are not strong enough to rip electrons out of atoms by main force. If they were, then the entire apparatus would have been instantly vaporized, as every atom was simultaneously ripped apart. The Raisin Cookie model leads to a simple explanation. We know that heat is the energy of random motion of atoms. The atoms in any object are therefore violently jostling each other all the time, and a few of these collisions are violent enough to knock electrons out of atoms. If this occurs near the surface of a solid object, the electron may come loose. Ordinarily, however, their loss of electrons is a self-limiting process. The loss of electrons leaves the object with a net positive charge, which attracts the lost sheep home to the fold. For objects immersed in air rather than vacuum, there will also be a balanced exchange of electrons between the air and the object. This interpretation explains the warm and friendly yellow glow of the vacuum tubes in an antique radio. To encourage the emission of electrons from the vacuum tube's cathodes, the cathodes are intentionally warmed up with little heater coils. Okay, again, there's some discussion questions and I won't read them. And I'm going to stop tonight before I do the summary. Hopefully I get to that. But actually this is great because in the summary there's definitions of words, which I kind of like. I should read this.